Hi there, my name is Marshall Cowning. I was in Group 7 for the combined spectral problems. This assignment made us use IR, 13C NMR, and 1H NMR to propose a structure for a molecule containing 9 carbon atoms and 12 hydrogen atoms. Going to our first slide, we are looking at the IR that was given to us. Analyzing this, we have found 6 different frequencies that intrigue us, and we can have functional groups that correlate with each of these frequencies. The first one I wanted to look at was going to be at 3100. This correlates with a functional group of an sp2 hybridized carbon to hydrogen bond. Next, I wanted to look at the frequency 3000. This peak correlates with the functional group of an sp3 hybridized carbon to hydrogen bond. The next frequency is going to be at 1650. This is going to show us a functional group that will be carbon-carbon double bond. The next one is going to be a frequency of 1450. This peak correlates with a functional group of a carbon-to-carbon single bond bend. This will help us deduce the structure later. The final frequency I wanted to look at was 1200, and this correlates with a functional group of C to C single bond. Moving to our next slide, this will be the 13C NMR that was given to us. There are 2 things you want to look at when analyzing these 13C NMRs. The first one is going to be symmetry, what I will come back to later, and the second is going to be dispersion of chemical shifts in relation to further or less downfield. So, when looking at chemical shifts, there is a range of 200 to 0. The less electrons or more electronegative atoms around the carbon, the higher magnetic field the nucleus is exposed to. Hence, it is harder to flip, and the ppm value is higher. So to explain this a little better, a higher chemical shift indicates a carbon atom in a more electron-deficient environment. This is usually around an electronegative atom like an oxygen or a double bond. A lower chemical shift indicates carbons with more electron density. So, looking at this NMR, we have 7 different peaks. And using what we know about dispersion, we're going to have 7 different bonding environments. This can also be used for symmetry now, as I first explained. A benzene ring would be the best structure for a symmetry that has 9 carbons but only gives us 7 signals. As a propylbenzene would have an alkane chain off of 1 carbon, and then there would be a plane of symmetry through the benzene ring, creating 2 groups of 2 symmetrical carbons, thus reducing the signal from 9 to 7. The first chemical shift is going to be at 125. This is going to be one of our carbon-to-carbon double bonds. The next one is going to be at 128. This is one of our symmetrical pairs. And this is going to be another carbon-to-carbon double bond on the benzene ring, as well as the next one at 128. This is going to be another carbon-to-carbon double bond symmetrical pair of carbons. These 2 together are going to reduce it from 9 to 7 signals. The next one at 142 is going to be the carbon-to-carbon double bond near the alkane chain, as it is going to be near a more electron-deficient environment. The final 3 are going to be your 3 respective pieces to the alkane chain from the benzene ring. The first one is going to be at 38. This is going to be the closest to the benzene ring. The next one is going to be at 25. This will be your second to furthest alkane chain. And the third one is going to be at 14. This will be your methyl group on the end of your propane chain connected to your benzene ring. Our final one we want to look at is the 1H NMR. You may notice that there are only 6 signals here, as opposed to our 13C NMR structure that was 7 signals. The main reason for this is that on the benzene ring, the carbon that is attached to the propane chain is going to have 4 bonds attached to it, thus not allowing a hydrogen to attach, which means there is no 1H signal coming from that carbon. So we lose one signal from 7 to 6. I will now explain the correlation to integration and multiplicity. Multiplicity is going to be the number of is going to be the number of hydrogens attached to adjacent carbon atoms. This is going to be your n+1 rule. So you would obviously take the number of adjacent atoms, add 1, and that will give you your multiplicity. For our chemical shift of 0.9, that would be a triplet. For our chemical shift of 1.6, that will be a sextet. For our chemical shift of 2.6, that will be a triplet. 7.0 singlet, 7.2 singlet, 7.4 singlet. The reason all of the chemical shifts in the 7s will be singlets is because all of the multiplicities on a carbon ring are going to be the same due to this symmetry that we talked about. Now when looking at integration, this is the number of protons that is responsible for the peak in each of the chemical shifts. So for the first 3, in 7.4, 7.2, and 7.0, these are all going to be 5 protons responsible for the peak. That is the 5H you see in the chart. The next one at 2.6 will have 2 hydrogens responsible for its peak, the same as the 1.6 chemical shift. And finally, our 0.9 chemical shift will have 3 hydrogens responsible for its peak. These are all ratios, so it would be 5 to 2 to 2 to 5. Or if you want to separate all of the 7s, it would be 5 to 5 to 5 to 2 to 2 to 3. And from these 3 graphs, we deduced that our final structure, as I said earlier, would be a propyl benzene. Thank you.